Okay, so it's my pleasure to introduce Stefan Henneking. Stefan right now is a research associate at the Oden Institute at UT Austin. He's working with Omar Gattas. I've known Stefan from PhD years. We were in the same group with Leszek Tengovic. Stefan is high of the finite element guy, and he did a lot of work for electromagnetics with the DPG method. But this is new research, as you can see. So he's going to talk about Bayesian inversion of an acoustic gravity model for predictive tsunami simulation. So, Stefan, please take it away.
Thank you, Socrates. Thank you for the introduction, and thanks for inviting me to give the seminar talk. I'd like to apologize in advance to everybody should you hear any fire alarm. Just got a notice from our building management. They'll be doing some fire alarm repairs today, so that's great timing. I hope it doesn't happen during the presentation. So the work that I'm presenting is joint work with Omar Gattas, and as the title suggests, we're interested in tsunami simulation. And one potential or certain tsunami hazard we're interested in is the Cascadia subduction zone. So this fault line is located off the Pacific Northwest coast of the US and Canada, as illustrated here in the picture. So what happens here is there is a divergent plate boundary between the Pacific plate, which is moving west, and the Juan de Fuca plate, which is pushed east. So there's a mantle upwelling here in the middle. And so the Juan de Fuca plate is moving at a rate of a few centimeters a year eastward into the North American continental plate, which itself is moving westward at a few centimeters a year. So they're meeting at the subduction zone, which is the red line here. And the Juan de Fuca plate is sliding underneath the North American plate here because it's denser and older also. Now, until the 1980s, it was believed that these plates are sliding freely alongside each other. And partly the reason was that there hasn't been any major earthquake event in this area in recorded history. But now it's known, or since the 1980s, it's known that actually in this red area, this red-purple area here, that these plates are actually locked with each other, which means they're not moving freely. Instead, there are friction forces that stop them from moving freely, and strain is accumulating. So this is depicted here in this slide. So on the left side, this is what it looks like when these plates are locked. So you have this gray slab, which indicates the Juan de Fuca plate coming from the west, which then interlocks at this orange area with the continental plate, and you can see that the North American plate is kind of being bulged upward, uplifted, and this happens at a rate of a few millimeters a year, so the continent is actually being lifted. Now this happens over the course of centuries until at some point the friction forces are overcome, the strain is too large, and then the whole energy is released either along a part of the subduction zone or the entire subduction zone, which is about 1,000 kilometers long. And the North American plate snaps back toward the ocean westwards, displacing a giant column of water upwards, which will result in a big surface gravity wave propagating eastwards onto shore and westwards into the Pacific Ocean, eventually toward Japan. So at the same time this happens, so this major earthquake and tsunami, the continental plate, the North American plate, would also be lowered by up to several meters, depending on how much uplift has accumulated over the years. So here's another depiction of the area. What you can see here is how, first of all, how large the subduction zone is, reaching from Northern California up to, Vancouver Island. A tsunami that's being generated along this fault line would reach, coastal areas here within 20 minutes. So there's a very large hazard for those coastal communities, including some major population centers. There's Victoria on Vancouver Island, which would be endangered because you have this inlet here, which is the Strait of Juan de Fuca, leading into the Salish Sea. And even Seattle would still be hit by, potentially hit by meters-high tsunami waves because you have this inlet here that kind of serves as a waveguide actually for the tsunami wave to go through and actually amplify the magnitude of the wave. So this is the potential hazard. How do we know that a tsunami event has even ever happened in this region? There's no earthquake in recorded history. So this was kind of found out in the 90s, in the 1990s. So there was a big storm system in the Pacific Northwest that uncovered these so-called ghost forests. So this is one off the coast of Oregon. This used to be a coastal forest. So what remains here are now the tree stumps. The theory is that this coastal forest during an earthquake event was lowered to the sea level, and the incoming tsunami wave destroyed the trees. Geologists went and they radiocarbon dated these trees, looked at the tree lines, the rings as they form, and found that, determined that sometime between the growing seasons of 1699 and 1700, these trees were destroyed. Coincidentally, around the same time, there was a geologist, or geophysicist actually in Japan, who looked into tsunami events that happened or were reported in towns in Japan along the coastline, and found there was one reported on the 26th of January in 1700. So now those two events are linked. So it's thought that there was a major rupture along the entire subduction zone, resulting in a magnitude 9 earthquake event, so a megathrust earthquake, that caused these growth forests these forests to be destroyed, as well as reaching the Japanese coast on that day. The other evidence, for example, is that they have now dug these pits, and all over, like in Oregon, Washington State. This is British Columbia, and you can find there that you have these layers here. On the bottom layer, here's a soily peat layer, on which a forest would have grown, which then was overlaid by sand brought in by a tsunami, and then a mud layer on top that comes from the tidal waves over time, and then a peaty layer again that supports vegetation on top. So these tsunamis have occurred regularly over certain intervals. I'll get to that in a moment. Here's just an overview of major earthquake events in the region, and with the region I mean the Ring of Fire in the Pacific. The red dots here are earthquake events. The larger the dot, the bigger the ruptures. So you have major earthquakes along the coast in Chile, Alaska, Japan, of course, Fukushima, we do remember, and then Indonesia, the 2004 Sumatra Andaman earthquake, we also all remember. So these are all the earthquake events happening in the region. And then the yellow triangles here are so-called dart buoys, which is one system that's in place for early warning. The buoy is kind of illustrated here on the right side. The way it works is that the seafloor sensor that records pressure data communicates with the buoy, and the buoy sends it to a satellite, which can then be used for early warning systems. Now, the problem with Cascadia is when you look at scenarios of how the Cascadia subduction zone might rupture and how an earthquake might occur, then this is one potential rupture event from a model and simulation here by Randy Levesque's group. The color in the plot here for different time snapshots for 1 minute, 2 minutes, 5 minutes, and so on is the surface wave height of the tsunami wave. And as you can see here, there are these 3 dots here are the actual locations of the dart buoys that are currently in place. And for this event, for the sample, it takes about 20 minutes for the first buoy to even register that there's a tsunami wave coming. And by that time, the first coastal areas would have already flooded from the incoming wave. So really, those dart buoys are not useful for forecasting or early warning in this instance. So you might ask, why did they even place them there west of that subduction zone? The reason is that when those buoys were placed, the hazard from this particular fault line wasn't known, and they were mainly placed there to do early warning in the case of incoming tsunamis from earthquake events in Alaska and maybe in Japan. And in those cases, they would work well, because when you have this long wavelength tsunami coming in the deep ocean, what you really measure is the hydrostatic pressure, and then it changes as the long wavelength tsunami goes through, and then you can fairly easily infer the source of the tsunami or the wave that's propagating and give a warning about that. Now, for the Cascadia fault line subduction zone, what's proposed, or this is not even the planning stage, but that's one potential strategy that could be in place, is a sensor network of 100 plus sensors that overlays this subduction zone all the way from Crescent City in Northern California to northern Washington State here. That would be sensors placed on the seafloor that are connected by fiber optic cable, and then report pressure data, which instantaneously transmits to the land-based facilities and can be used for early warning. So this is the kind of data that we have in mind when we work on the model, and the inverse model that we're interested in is basically near field data from close to where the rupture event happens. Just in terms of the evidence, I mentioned that we expect, the reason why we're doing this is because we expect another earthquake to happen eventually. So when you look at major ruptures, that the estimated times at which this happens from other evidence that has been uncovered, you see that it has occurred on regular intervals, about every 300 to 700 years or so. There has been a major rupture in this area. If you add 300 to 1700, close to today, so might happen any day. The current estimate is that 37% probability of a magnitude 8.2 plus event within the next 50 years. So this would be a partial rupture along the subduction zone, whereas there's also a 10 to 15% probability estimate for the entire zone to rupture, which would result in a megathrust 9 plus magnitude event and large tsunami following it. So a lot of the models that currently used are relying on shallow water equations, which work fairly well for the tsunami propagation itself. However, for inference from this pressure data, that doesn't work because it doesn't capture the dynamics of the pressure waves that come from the earthquake itself. And I'll show you an example of that in just a moment. The goals that we have with our work is we want to use these pressure waves that originate from the earthquake, from the excitation from the seafloor movement that causes pressure waves, use that pressure data to invert for the seafloor motion, and then forecast for the tsunami. We want to do this in the Bayesian framework to be able to quantify uncertainties. We would like to do this in real time, which means within a few minutes, to use it for early warning. We want to use high fidelity models, so PDE-based models, rather than just fitting it to data or something like that. And eventually, we would like to also provide guidance on where to place sensors in order to have a good model for inference and maximize the information gain. Because as you can imagine, those sensors are expensive to operate, so there's a limited resource that we have. Here's an example of a near field pressure reading. This is from a 2003 Japan event. And you can see that the time axis here covers 2 hours roughly. On the x-axis, the y-axis is the pressure scale. And so before the earthquake happens here, you basically get a reading of the hydrostatic pressure. And then, what you would see when the seafloor is uplifted and the tsunami wave propagates away is this drop in hydrostatic pressure to a lower level because the seafloor has been uplifted at this point. However, during this entire time, which 20, 30 minutes, you have these high magnitude oscillation, pressure waves, hydroacoustic waves oscillating. So you really have to have a model that captures those dynamics if you want to use this kind of data to infer the seafloor motion and infer the source of the tsunami. So this is the main idea, what I just mentioned. So it's a time-dependent parameter field that we're trying to infer in our inverse model. For that, we're using a linearized version of an acoustic gravity model. So it's an acoustic wave propagation model coupled to a surface gravity wave boundary condition that models the tsunami wave in the compressible ocean. And of course, the potential advantage would here be that we can do earlier and more accurate forecasting using this near field data. Challenges, well, there are plenty of those. The first one that comes to mind is simply the computational tractability of it. So now, instead of the 2D space domain that you have in the shallow water equations model, you're dealing with a 3D space domain plus time. You have to, in this case, discretize and resolve the hydroacoustic waves. They have a relatively short wavelength as compared to a surface gravity wave. If you think about an earthquake that excites at a 1 Hertz frequency, some energy, and the acoustic waves propagate roughly at 1500 meters per second, so that would translate into a wavelength of 1500 meters that needs to be resolved as compared to a much slower propagating and longer wavelength tsunami wave. The parameter dimension is also very large, as you will see later. So this would be a 2D space plus time parameter dimension, sort of on the seafloor boundary of the domain. So let me go to a forward model. For everything I'm showing today, numerical results, I'm going to stick to a 2D model problem. So this is 2D space plus time. We haven't done the 3D implementation. I'll talk about that at the very end a little bit. But this should give you the idea. So all of this is work in progress and sort of proof of concept. So at the bottom, at the C bottom here, we have the bathymetry denoted by B, and then the quantity of interest, the source of the change of the bathymetry over time, which is the seafloor motion. At the top, we have the wave height that's being modeled at the sea surface, which uses the letter eta. The PDE model itself is a mixed formulation derived from conservation of mass and momentum. We have two unknowns. The velocity is a vector-valued unknown, and the pressure is a scalar-valued unknown. We have rho, which is the density, and k is the modulus. And the interesting part maybe here are the boundary conditions, if you're not familiar with these types of models. So there's a linearized boundary condition, an ODE type boundary condition at the surface, which is the second part here where eta is related to the velocity, the normal velocity, and eta is the sea surface height. The source term that drives the problem is the bathymetry change. So in the forward model, it's assumed that this dB over dt is given here. This is the change of the bathymetry over time. And that will be also in the inverse model, the parameter field that we infer for. On the outer boundaries, left and right, horizontal boundaries, we are having to introduce some artificial boundary conditions. We can't model the ocean forever. So we, in the first example here, I'm going to show you first order absorbing boundary conditions, impedance type boundary conditions. I'll show you that they don't work quite as well. And then I want to show you how the PML implementation that I have worked on. So let me, okay, let me go to the formulation here. So first we non-dimensionalize, and then we do want to discretize this problem with finite elements in space and finite differences in time. Right now I'm sticking to the continuous formulation here. So what we're doing is we're integrating the second equation by parts, which gives a less common formulation than the one if you integrate the first one by parts. If you integrate the second equation by parts, you move the divergence from the velocity space to become a gradient on the test function v here. So the test functions are tau and v. So this is the weak formulation in the continuous space-time setting. And then what you basically have is you have a vector value velocity space that can be discontinuous in space and a pressure space that has to be continuous in space. So this is the weak formulation. You can see that if we do it this way, we are able to build all of the boundary conditions into the model directly and actually eliminate this additional unknown eta because we can relate it directly to the pressure on the sea surface. And this is the first term that comes up here, which brings in the pressure derivative and time on the boundary itself. So all of the boundary terms are here, and the load is here on the right-hand side, which involves the source term that we assume is given in the forward model. Yeah, I don't want to go into this in too much detail here. This is just the semi-discrete formulation. For example, this is an example here with the Crank-Nicholson time stepping. Of course, you can do explicit methods as well. Essentially, you just have a time stepping scheme, and then each time step you're solving a finite element system for this bilinear form and this load. So this will be discretized with finite elements, conforming finite elements, and we are able to do this with the Galerkin method here. You have a symmetric functional setting because we're working with this mixed formulation. Now, to verify that this method, that we've proposed here works, we want to verify that we obtain convergence rates for analytical solutions. So one thing you can do is fix the domain and excite certain frequencies. So in a fixed domain with no outgoing boundary conditions, but a Dirichlet boundary condition on the side, for any frequency you choose, there's certain modes that can propagate. The modal solutions are shown here. And for any of those frequency, there's exactly one surface gravity wave mode that propagates and a limited number of propagating acoustic gravity wave modes. So those are the hydroacoustic waves that propagate. And then there's an infinite number of decaying or evanescent acoustic modes, which we're not so interested in. So these first two types of modes is what we want to be able to capture. So doing some convergence tests, on the left side here is a low order case for the surface gravity wave mode. So I'm using, as I mentioned, we have a continuous space for the pressure, a discontinuous space for the velocity. So I'm using conforming, Lagrangian elements in this case. So there's a second order element for the pressure and the first order discontinuous element for the velocity space. And so what you get is then the expected second order convergence rate for both of these errors that are measured in the corresponding H1 and L2 norm. And then for the first acoustic gravity wave mode that's being shown here, same thing. Here I'm showing the second order case and then also the third order case, attaining all the convergence rates as expected. Okay, one quick numerical example for the forward model. Here on the left side is an illustration. So this example uses sort of like the simplest model problem that's common in the literature. It's a Gaussian seafloor deformation, a Gaussian bump, so to say, on the seafloor. So, just bulging upward by a few meters. And, this is the seafloor bottom. What's plotted here is the pressure. The pressure is on a scale of meters, so it's kind of like converted to a scale of meters. The reason for that is because then you can read the tsunami wave height directly at the surface here. So the sea surface is at the top, and what you can see is as the pressure waves are oscillating, the sea surface boundary condition lets the tsunami wave build at the surface, and then over time gravity acts on it and it separates, and you have two tsunami waves propagating east and west. On the right-hand side here are two synthetic observers. There's no noise or anything, just to show you what a signal can look like in an idealized scenario like this. There's a near-field observation where you can see you have the blue line here is the bottom pressure, the red line is the sea surface height at this location, and the yellow is the bottom displacement at the location. So this is in the near field, 5 kilometers from the epicenter of the movement of the seafloor. And you can see here that over time, what happens is that as the tsunami wave propagates away, you have this lowering in the hydrostatic pressure. So that is where the curve goes lower here. The far field observation, and that shows you why it's easy to infer a propagating tsunami wave in the far field. If you just look at the mean of the pressure here, you get exactly the sea surface height. Because all you have is basically a pressure wave corresponding to the propagating tsunami wave going through as the tsunami propagates along. So this was a very simple numerical example. Now I want to go to a little bit more technical part, even though I'm not going into all of the details, but that's the PML formulation. So I mentioned I first did the impedance boundary condition, which, if you're familiar with it, you can already imagine why it might not work so well, either because the wave angles aren't close to normal angles at the boundary, or because we have actually two wave speeds here. We have the acoustic wave speed and the surface gravity wave speed. So that's an issue with the impedance boundary condition. So what I did is try out a PML formulation. Many of you are familiar with PMLs. I know FEM supports PMLs as well. So the way this works is by introducing a layer here, an absorbing layer that serves to absorb the outgoing waves, avoid artificial reflections. And there's something really interesting here. So we begin by doing sort of one standard methodology is to introduce a complex coordinate stretching. So inside of the PML area, we replace the real coordinates with the complex coordinate, where we have a so-called stretching function. The stretching function serves in order to, when we pull back to real coordinates, then absorb the outgoing wave modes so that they decay in an exponential way. So you can do this for the outgoing wave modes, not for the incoming ones. But usually the way I've learned to apply this has been in the frequency domain setting. So that's what I was familiar with. So for me, this was new because now we have a time domain setting, and I hadn't done a PML there before. So what did I do here in order to realize the PML in the time domain? So the first step was to take the time domain formulation and Fourier transform it into the frequency domain and apply the complex coordinate stretching there. Once applied, I would do the usual pullback maps through Pure transformations, pull back the complex coordinate to the real coordinate system in the frequency domain. And what you then notice is that once you do this, if you want to go back and reverse to the time domain, what pops up is this additional term, like a 1 over I omega, which introduces an additional time derivative into the equations. And reversing to the time domain, what you find is once you've gone through the algebra, is that you actually get a third equation here, and a third unknown that exists in the PML only. So this is an auxiliary differential equation. We have this new unknown psi, and this equation is solved only inside of the PML. Additionally, you have also terms that pop up here that involve these sigma x terms, which are absorbing functions, which also are non-zero only inside the PML region. Importantly, we also have to modify the boundary condition because that involves the surface gravity wave. So that also, if you go through the same system, same thing, same process, you see that it has this additional term coming in that's non-zero inside the PML region. The continuous weak form for this problem then is shown here. So all of the orange terms are introduced because of the PML formulation. So that's the difference to the previous standard formulation with the absorbing term. Importantly, though, all of these orange terms that we introduce, they all vanish once you are not inside the PML, which means you're consistent in the way that if you're inside the computational domain of interest, you haven't changed your formulation. A few results quick on the PML. So actually, I was quite happy to see that it works well. Here's an example for far field observations. So the pressure is plotted for a reference solution, which is the blue line. And then different other, there's the Dirichlet boundary condition, impedance boundary condition, PML are shown as well. And, the far field observation is where you're having sort of an observation, a sensor close to that artificial boundary. So you would expect to see artificial reflections and errors early on in your computation if your boundary condition is not, is not working well. And that's exactly what we see here. So you see the reference solution is the blue line, and the yellow line, which is the impedance, the yellow dotted line is the impedance boundary condition solution. You see it's quite different. It diverges very quickly from the reference solution, whereas the PML solution sits right on top. If you go to later observations, you keep simulating this for a longer time, you find that the PML has to be a bit larger. 5 kilometers is not enough. This is likely because you have the surface gravity wave then coming in with more energy. And so the 10-kilometer PML nails it, though, and sits right on top of the reference solution, even for longer time frames. In the near field, it doesn't really matter too much in the very beginning which boundary condition you have, because it takes time for the wave to propagate out to the boundary to be potentially artificially reflected. So in the beginning, none of the boundary conditions here have an impact on the solution. Everything is similar to the reference solution. But if you go to longer time horizons, the same thing again. The PML solution is right on top of the reference solution, whereas the impedance boundary condition also gets artificial reflections back to the near field observers. Okay, so now let me move on to the inverse model. First to state the inverse problem, and I mentioned it already in the beginning. So we assume that we have pressure recordings from the seafloor, from sensors on the seafloor that are given potentially noisy observations. And what we want is we want to infer the seafloor motion in the subduction zone. So that's the inverse problem. To give you a few definitions first, so the state is comprised of the velocity, pressure, and surface height unknown. The parameter field is denoted by M. M here simply denotes the source term for the forward problem, so that's the time derivative of the bathymetry, so the change of the bathymetry over time. The data, the observational data that we assume is collected and is used for the inference is denoted by D, and it comes from a observation space. And we have two scenarios here. So there's an observation operator mapping from the state space to the data, to the observation space. The first one is the idealized scenario of having full observation. So this is basically the scenario where you assume you have the entire seafloor carpeted with sensors, so you have perfect knowledge of pressure everywhere. Of course, that's not realistic, but it serves as an upper bound to what is attainable, even if you had those resources. The more realistic scenario is that there's a distinct number of pressure sensors that are placed somewhere. So these are then point-wise sparse observations on the seafloor, and they can be sparse in space as well as sparse in time, depending on the sampling rate and how quickly how many pressure recordings you do per second. The so-called parameter-to-observable map is denoted by F. So this is the map which maps the parameter M to the observables, the data space. So through this observation operator, where so this mapping involves the solving the PDE forward operator, and then doing the observations. In this problem, if you've paid close attention, you've maybe noticed that everything we've done here, and this will become very important later, has been linear so far. So in particular, the source term shows up linearly in the observations. So that means this parameter to observation map, to observable map F, is in fact a linear mapping. Okay, as I mentioned, we want to do this in the Bayesian setting. Here, the Bayes rule is given in the infinite dimensional setting. So this is the Radon-Nikodym derivative of the posterior measure over the prior measure, which is proportional to the likelihood of the data conditioned on the parameter field M. For the prior, we're using a Gaussian, and for now, we're simply using the Gaussian here is centered at some M prior and weighted with an inverse covariance matrix gamma prior. And for the covariance, which is derived from a Matern covariance operator, we are using an inverse elliptic operator. So it's kind of like a Poisson type operator here. But it doesn't have to be to the -1. It could be a higher one depending on the dimension we're working with. We need to adjust the gamma here for bounded pointwise variance. But it's basically an inverse elliptic operator that serves to smooth the data. And if you're familiar with deterministic inversion, then you can think of these alphas that occur here as regularization parameters. For the likelihood, we're introducing some observational noise. So this is additive observational noise, which we assume is also normally distributed and IID. So giving the term here, so this, again, if you interpret in terms of deterministic setting, then this corresponds to a data misfit weighted by the inverse noise covariance. And given these terms, we can then actually, define what the posterior measure looks like by the expression down here. It is given, and I'll go into a little bit more detail on the next slide on that. So the posterior measure for this problem is then in fact also a Gaussian, and that's because we have a linear inverse problem. So we have a linear inverse problem, we have a Gaussian prior, we have the additive Gaussian noise. So all of that enables us to actually characterize the posterior measure as this Gaussian, which is centered at the map point. The map point is the maximum a posterior point, so that's the point that maximizes the posterior distribution. And you can also define it as the minimizer for the negative log of the posterior as done here. And what that enables you to do is that you can now concisely write down how to compute this map point. So this corresponds to solving a deterministic inverse problem. So this is the mean of the posterior, which is the solution of a deterministic problem, where on the left side here, the operator that would correspond to the Hessian, so the Hessian of the data misfit and the Hessian of the regularization. And this is a linear system which we can solve. It's a positive definite system in this case. And the right-hand side here depends, of course, on the data. And this is how you can obtain the map point. Now, the posterior covariance is what we're interested in if we want to define uncertainties. And that one's given by the inverse Hessian, which itself is, of course, also a dense matrix. So this is what I'll talk about a little bit on the next slide also. The posterior covariance here, we're mostly interested in the diagonal, in the trace, or the diagonal values, which are the pointwise variance values. Okay, so having defined these or characterized the posterior, we can now go and start computing. The way we compute the Hessian here is through adjoint-based methodology. So we form the Lagrangian, we take first variations with respect to the state, and we derive the adjoint system, which is shown on the next slide here. The adjoint variables, adjoint velocity is tau, the adjoint pressure is v, and you have the adjoint mixed formulation shown here with boundary conditions, which mostly look similar to what you saw in the forward model. One difference here is that now the source term here includes sort of a data misfit term weighted by the noise covariance. Remember B is the observation operator, and the data shows up here, and P is the pressure from the state solution. One key difference in the adjoint system as compared to the forward model is that instead of initial conditions, we now have terminal conditions. So in the adjoint system, we have to do time stepping backwards. So in this case, we're using homogeneous terminal conditions. So the adjoint system is discretized in a similar way. Here's the continuous weak formulation. Again, we integrate by parts in the same way to obtain the same functional setting as in the forward model. So now we have, again, this continuous vector valued space for tau and a continuous scalar valued space for v, and then the corresponding test functions sigma and q. We solve or discretize then this formulation here again with finite differences in time and finite elements in space, conforming finite elements in space. What we're then interested in order to solve for the map point, as I mentioned, the operator on the left-hand side is the Hessian. So in order to solve this, we can't actually compute the Hessian matrix because it's much too large for realistic problems. So what we can do though is we want to be able to apply the Hessian to a vector. So the action of the Hessian on a vector, that one's derived by taking the first variations with regard to the parameter. So applying the Hessian to parameter m involves the parameter itself as well as the adjoint pressure solution. And so what that means is that in a sense we can obtain this Hessian action by a pair of forward adjoint solves. So solving the forward problem given the parameter m for the state solution. The state solution involves the pressure P, which is necessary for the source and the adjoint problem. We solve the adjoint problem for tau v and sigma s, which is the adjoint surface wave height, and the adjoint pressure V enters the Hessian action here, which we can then evaluate. And so we can use an iterative method to solve for the map point. And I want to show some results to illustrate how this method works. Instead of using the single Gaussian bump from the first example, I'm doing something slightly more complicated, introducing some higher frequency content by using 3 superimposed Gaussians. 2 of them have a smaller spatial width, which introduces these higher frequencies into the excitation. Here is the first result. This is the idealized scenario. So what here's where we're using a model problem that where we use full observation, so we have perfect knowledge of the pressure everywhere and no noise. So this is the best case scenario. The parameter dimension is 6,500 in this case. And what we're trying to infer, remember, is the parameter field, which is a time-dependent field. So it's the bathymetry motion over time. If you time integrate this parameter field, then what you get is the total bathymetry change. And so this is basically the black dotted line here is the true total bathymetry change in this example, and the red line is the inferred total bathymetry change. And you can see it does very well in the inference in terms of the smooth component. However, you do miss the higher frequency component here. I'll say a few things about that later. So even with perfect knowledge of the data and everything, this is still smoothed out, and that's because some of those higher frequency data are associated with modes that are unstable in the reconstruction, so this is smoothed out by the prior. In the bottom here, you see the actual pressure reconstruction. This is what we are trying to match. In this case, no noise. Their observations are overlying with the truth, and then the reconstruction is actually more or less perfect, exactly overlying with the observations. Second case, now we're going to the sparse observations case. Again, let's start with no noise. And now I'm starting also in these cases to show the uncertainty. So what you see here is the 95% confidence interval. So the red line in the inference corresponds to the map point. The orange dots are the sensor locations. So we're using 9 equidistant sensors in this case. And then the orange cone, the orange area around the map point, corresponds to the 95% confidence interval. And again, as you can see in the inference, the smooth component of the seafloor motion is inferred very well. However, the higher frequency content or higher frequency motion is smoothed out and not inferred entirely. Similar at the bottom, pressure reconstruction, again, no noise case, so the observations overlie with the truth, and then the inverted solution, pretty much matches exactly the pressure solution at the observation points, but of course it does not reconstruct the more oscillatory components, where there is no data recorded. Here is, for the same example, the recordings of two pressure sensors over time overlaid with the inverted solutions observations. Again, in the no noise case, we get perfect reconstruction at these sensors. And maybe the more important thing, what we're actually interested in isn't just the pressure reconstruction, or the sea surface, the seafloor motion, but we want to know the tsunami wave that's propagating. So we want to get the tsunami wave height correct. And so when you look at the reconstruction of the tsunami wave height, you actually find that even though the higher frequency components in the pressure reconstruction aren't matched, it's the smooth components that dominate, that drive the tsunami surface gravity wave, how it's building up. So we get a very good reconstruction of the tsunami wave and how high it is, even if we don't get the higher frequency, if you're not able to reconstruct the higher frequency components. Now let me go to the noise cases. On the top row here, you have a case with 1% relative observational noise. On the bottom row, you have the case with 5% relative observational noise. And actually, these are kind of like worst case scenarios, because when I say relative observational noise, we take 5% here from the maximum data observed and apply that everywhere. So even in data regions where the pressure is very low, we have we have fairly large observational noise. And what you see here is that same as before, the smooth component in both cases is still nicely reconstructed. Actually, we do have. You can of course see that the uncertainty becomes larger for the case where more noise is there, but you also can see that uncertainty is smallest near the observation points and then larger in between the observation points as expected. The bottom pressure is still nicely reconstructed at the observation points. Of course, you don't want to overfit that data, so the prior is needed to smooth out some of that noisy data. And as with the no noise example, of course, the higher frequency content here is not reconstructed. So for the 1% noise example, you also see the reconstruction of the pressure at two sensor locations. So this is really what we're trying to match in the inversion. And again, in this case, even with this 1% error, 1% noise, we have very little error in the reconstruction of the tsunami gravity wave, which is a good signal that we don't make significant errors by not being able to infer those higher frequency components. Here's the 5% error case. You see the data is much more noisy. The observations, which is the blue dotted line at those two sensors, are jumping around quite a bit. And of course, the inferred solution, the reconstruction of the pressure, is also a little bit more prone to errors here because of that noisy data, but you see it's nicely smoothed out, avoiding some of that overfitting to that noisy data. And even in this case, you still get a fairly good reconstruction of the tsunami gravity wave, getting close to the actual wave height of the model. Okay, so I've talked about the proof of concept and have shown you results for the 2D problem. Now, what do we need to actually make this happen for the entire Cascadia subduction zone in a 3D space plus time setting? So really what we need here is we need to be able to compute the map point and the posterior covariance, or at least the diagonal of the posterior covariance, to get those uncertainties in the inferred parameter field. And the reason why we might hope to be able to do this fast, meaning being able to do quick predictions in the case of an earthquake event, is because all of these orange terms here, because the problem is a linear inverse problem, all of these orange terms can be pre-computed. None of these things are dependent upon the data. The data only shows up here, D, in the computation of the map point. And what you basically need is a pre-computed compact representation of this operator that can be applied to the data stream that is coming in from the sensors in the event of an earthquake. So that sounds, of course, easier than it actually is. We have a very large problem size here. an estimate would be that for Cascadia, we might have something like 10 to the 10 states. We have 10 to the 9 parameters, so a billion parameters in the 3D problem, and 10 to the 5 data. So, just storing the parameter to observable map would require 1 petabyte of storage, not even speaking, the hashing, of course, would be large, and so on and so forth. And we wouldn't be able to solve these or pre-compute the full map. So that would be intractable. So what we need is a compact representation. So this is kind of where we're at right now. Now, the tricky part is that while problems of this kind of size or somewhere close to this size have been done before, they usually exploit the structure in a very large way, the structure of the problem. And that's something we will need to do here as well. So typically for an ill-post inverse problem like this, in geosciences, often you can exploit the low-rank structure of the Hessian of the data misfit. You basically determine the effective rank of that operator, and then you use a randomized eigensolver to compute such a compact representation, which can then be used to rapidly apply it to vectors in a much faster time. One example I'll go over very quickly here, I was not involved with this, is the work on the Antarctic ice shield model. Okay, my presentation here is a little laggy. Okay, so this was work I was not involved with, but that Omar and his postdocs and students have worked on for many years. So this was based on some surface velocity observations made by satellites, reconstructing or inferring, inferring the boundary condition on the bottom of that ice shield. Finding out whether it's like a no slip or free slip or something in between boundary that you have there. And you see here the map point estimate and the uncertainties involved. The reason they were able to do this, because this is also a very, very large problem, is exactly because of the being able to exploit this low rank structure. And that's very typical for many applications. So this problem, which it's solving a Stokes problem, a nonlinear Stokes problem actually. Here what you see here plotted on the top left are the eigenvalues of the Hessian of the data misfit for the case here of 1.2 million parameters. And what you see is that over the course of the first 4,000 eigenvalues, so this spectrum of that Hessian of the data misfit decays so rapidly. So you have 8 orders of magnitude decay in the first 4,000 eigenvalues. And then everything that follows pretty much here is just noise. So that's taken care of by the prior. So you don't try to reconstruct modes associated with this data. So really the informative modes that you're trying to instruct, the informative data that you're trying to reconstruct modes for are associated with those first 4,000 modes here. And that means you cut off most of the work, and you really just need an operator of that size, of size 4,000 by 4,000 for to represent the effective rank of the Hessian. Importantly, also this this overcomes the curse of dimensionality, because what you can see here is that as you go from 400,000 to 1.2 million parameters, actually the spectrum doesn't change at all. So once you have reached a certain discretization threshold, or discretized fine enough, even if you go further and discretize more finely your parameter field, the spectrum still decays at the same rate, and so you don't have to increase the number of eigenvalues that you consider. So that's not the problem we're solving. Unfortunately, the problem we're solving is this one here. So here you see the Hessian of the tsunami problem. On the left side, you have the full observation case. On the right side, you have the pointwise sparse observation case. And what you see here is that in both cases, the eigenvalues decay very slowly. And really only in this case, you have a dimension of 3,300 in this model problem. Only the last 10% or so of those eigenvalues you could get rid of by saying, well, these are noisy, we're not going to be able to reconstruct those modes anyway, because that would be unstable. But the first 90%, we might be able to reconstruct. So the data are very informative in this problem. The same is true for the sparse observations. The rank, of course, is limited by the data dimension here, which is much smaller than in the full observational case. So in this case, same thing, you can cut off the tail of this, which is maybe 10%, but the first 90% you should really retain. So that's great news. As a scientist, we're able to infer a lot of information from the data we collect, but it's a headache for a mathematician because, we need to consider all of these modes. So what do we do? Well, we really don't quite know yet. We're still working on this. There are some modest successes that Omar's group has had, Nick Algier and some others in the group that have worked on hyperbolic problems. So this is really, why so much information is retained, because we have a problem of hyperbolic nature here. None of the current approaches quite scale to the level or are applicable directly to what we are trying to do. So we do still need some new thinking and approaches here to make this feasible for the large scale problem that we hope to solve. And with that, let me summarize here and finish and just give a quick outlook on ongoing and future work. So I talked about the fast solver, which will require new work to be done. One thing I left out completely is the parameter field that we obtain is not the not the forecast that we want to make. What we want to forecast is the inundation of the tsunami. Where is it going to flood and so on. So we still need to couple eventually or forward propagate the map point and the uncertainties into a tsunami propagation model, which would be a nonlinear shallow water equations model to propagate the tsunami to the coastline. For that, we also would need something like the reduced order model, something that works faster because there wouldn't be any time to solve the actual full equations here. The actual operator would be too expensive to solve if you want to use it for early warning. I mentioned the OED problem for placing of sensors. And then finally, what I want to mention here, so everything you saw today in those computations, this was all, as I mentioned, proof of concept, 2D spatial computations I did in Phoenix. The 3D implementation we are planning to do in MFEM, hoping to do in MFEM, so we're actually thinking about getting started with that later on this month. And maybe this is a great place for a discussion to start. There are lots of MFEM experts in the audience today, so I'd be really interested to hear what you think, how realizable this kind of problem on a large scale is in MFEM, maybe what pieces are already there and what pieces might be missing and still need to be supported and worked on in MFEM to be able to do that. So with that, let me close here and thank you for coming to the seminar and thanks again for hosting me. And yay, no fire alarm.
Thank you very much, Stefan. That was a very, very nice talk.
Thank you, Sir.
Let me ask the audience for any questions, comments, questions. Okay, let me start by one question. Very simple one. So realistically, what is the hope in terms of how early can you would like to predict the tsunami? You said like it takes 20 minutes to reach the coast, right?
Yeah, that's a good question. So there are multiple answers to this, but with the model that I've talked about here, you'd still have to wait for the hydroacoustic waves to reach these sensors and then take that data. Maybe you wait 10 seconds, 20 seconds. You want to be able to plug that data into the computation and then ideally warn within the first minute. So, send out warnings about the tsunami hazard. Also, like one aspect of this is not just the early warning, but when you look at these large, because the region is so large, one important thing will be to inform first responders which areas are going to be most flooded and impacted by, so you can respond correspondingly. But yeah, so ideally, within the first minute to send out warnings, and that would go through, for example, through cell phones. Of course, what you could try to do, this would be a much more difficult thing to do. Omar has talked about this before, but that's just theory right now. You could try to couple the model that we have to a model of the, the seismic. Well, basically, you would have to couple it to an elastic wave equation inside of the plate itself, and then you could try to solve to forward propagate the seismic problem and come up with a shake map and see, where would the earthquake be occurring. And that would be really valuable information for first responders as well as for early warning. Potentially, if you were able to have a very fast map that maps from the data that you collect to the seismic activity, you could even send out warnings before a seismic wave reaches further regions like Seattle. But yeah, so the early warnings is definitely one aspect, and another one is the response to the event itself.
Right.
Really nice talk, Stefan. For the 3D implementation, what tools would you expect to have already in FEM? What do you need, and what do you think? What for example is not present in Phoenix?
So in Phoenix, for the model problem, I ended up coding quite a few things myself. Just in terms of some of the operators I was showing and functionality. So one thing that I don't know if MFEM has something like this yet that I think eventually would be of interest. I'm not sure if you're familiar with HippieLib. That's a library that is implemented on top of Phoenix by Umberto Villa and Omar and some other collaborators. That basically helps with let me see, some of these approaches I was mentioning here, like these creating these low-rank spectral decompositions of a Hessian through a randomized eigensolver. So basically tools like that built on top that make it easier to build some of these compact representations based on existing algorithms. Having said that, for this particular problem in Phoenix, I've ended up implementing most of it myself because the time dependency is something a little bit non-standard again. If you do it only in space, you have one discretization, you have one problem, and then most of these things have been implemented in HippieLib. So that's, I tried that for time invariant problems, but for the time dependent problem here at hand, I had to implement quite a few things myself. But in terms of discretization, MFEM has everything that's there. I've never gone and tried the meshing capabilities and so on, but I imagine that wouldn't be an issue for something like Cascadia to come up with a mesh for that. So I was thinking mostly about support or tools that might make it easier to solve inverse problems in the Bayesian framework.
So meshing should not be an issue at all. We worked with Umberto before. Umberto is one of the MFEM developers. He spent actually several summers here. But we don't have such low-rank spectral decompositions with randomized eigenvectors. I can imagine maybe there could be a connection with HippieLib also for MFEM. We just don't have it. Do you expect the Hessian, for example, do you need something like automatic differentiation, or is it you have an explicit formula for the Hessian that you kind of have differentiated yourself?
Right now, I implemented it myself. I think AD is definitely useful for these types of problems. For the majority of people, they like using AD. I'm not sure, in terms of this kind of problem, when you have the very large scale, I personally prefer to just derive all of the adjoint based systems myself, because then there's more opportunity to implement and optimize those computations, and I think that would end up being faster than doing automatic differentiation, especially since the system here isn't too complex to go through all of that by hand and just implement it ourselves. So I think in this instant, for this problem, I actually would not need automatic differentiation.
Yeah.
But I think the majority of people probably would like to use that in the context of Bayesian inversion. Yeah. I think the majority of our group is now using AD to some extent.
Okay, let me ask another question. In terms of large-scale computations, how large have you taken this? How large do you want to take it?
As large as it goes. Well, you do know how Omar is. He likes to push it to the limit of what the supercomputers can do. Yeah.
So what have you done so far?
Oh, so far we've only done the proof of concept. We haven't implemented the 3D problem at all. That's what I was saying. We just getting started on this year for the 3D implementation. But if we wanted to do that, as I mentioned here, the parameter dimension alone would be about 1 billion, maybe even larger. And the state dimension is somewhere around 10 to 100 billion. So fairly large. And you of course need to solve those problems many times over in order to solve the inverse problem. Especially if we were to do something like an optimization problem for placing sensors at the end, it would involve not just one solving or one solution of whatever we're doing, but many solutions. But yeah, probably as large as we can do.
Cool.
There is a question in the chat. The reasons that you choose FEM for the 3D implementation.
Oh, that's a good point. Well, we talked about different options. One of the main reasons is that FEM is scalable. So we know it's scalable to large computers. The second aspect is that I and a few others in our group are familiar with FEM already. And the third aspect, I think maybe the most important one, is that it's one of the libraries that has the community behind it, and the developers, many of whom are here or were here today. So, which means if we need something for a big project, we can always put an issue in, and we know it's going to be worked on if it's important. And also we know people like you, Socrates, or like Zanio, we can ask for advice if we don't make if I have trouble with implementing something. So sort of like the support that's there, the whole framework. I think that's those three things are the main aspects. So scalability and the community behind it, and that we have also some familiarity implementing an FEM within our own group already.